You are standing on a planet. The ground beneath your feet feels solid. Above you, the night sky blazes with stars, thousands of them. You can trace the river of the Milky Way across the darkness, that band of ancient light that has guided sailors, poets, and dreamers for as long as humans have looked up. This is not your reality. In your reality, that night, sky is black. Not dark, black. The kind of black that swallows your gaze and returns nothing. You strain your eyes, searching for light, for something, for anything. And there is nothing there. No stars, no constellations, no galaxy overhead. Just an endless, empty void stretching in every direction, as if the universe forgot you existed. Welcome to the loneliest place in the observable universe. Imagine for a moment that the Milky Way, our home, had formed somewhere else, not here, nestled among the galactic filaments, swimming in a sea of neighboring galaxies, but at the center of an impossible emptiness, a region of space so vast and so vacant that the nearest significant galaxy lies over 100 million light years away. This is not science fiction. This place exists. In 1981, astronomer Robert Kirshner was working at the University of Michigan on something that sounds almost mundane, measuring how fast distant galaxies are moving away from us. By calculating what's called the redshift of galactic light, the way light stretches toward the red end of the spectrum as its source recedes, Kirshner and his colleagues were building a three-dimensional map of the universe. This was painstaking work. Kirshner, along with Augustus Oehmler Jr., Paul Schechter, and Stephen Schechtman, was conducting a redshift survey, systematically measuring the light from galaxies across different regions of the sky and using those measurements to plot their three-dimensional positions. At the time, astronomers were still building their understanding of the large-scale structure of the universe. They knew galaxies existed. They knew galaxies clustered together. But the full picture of the cosmic web, with its filaments and voids and superclusters, was only beginning to emerge. It should have been routine. They expected to find galaxies everywhere they looked, scattered across space like grains of sand on an infinite beach. That's what the prevailing theory predicted. That's what all their earlier observations had shown. The universe, on large scales, was supposed to be roughly homogeneous, the same everywhere you look. But as their map took shape, something strange appeared. In the direction of the constellation Boötes, the data showed a gap, a blank spot. At first, they assumed it was an error, maybe a calibration issue with their instruments, maybe a problem with the calculations, maybe some systematic bias in the way they were selecting targets. They checked and rechecked. The gap remained. What they had found was not an error. It was a hole in the universe. The team published their findings in a paper with a deliberately cautious title, "A million cubic megaparsec void in Boötes." The question mark was significant. They weren't entirely certain what they had found. The void was so large, so empty, that it seemed almost impossible. Could the universe really contain a region this devoid of galaxies? The answer, confirmed by subsequent observations, was yes. At first, astronomers found only a handful of galaxies within the void, perhaps 8, scattered across an unimaginable expanse. Later surveys revealed more, eventually bringing the count to around 60. But even 60 galaxies in a region that should contain 2,000 represents an astonishing emptiness. The Boötes Void, quickly nicknamed the Great Nothing, had earned its name. The Boötes Void is almost impossible to comprehend. It spans roughly 330 million light-years across. To put that in perspective, a single light-year is about 6 trillion miles. The distance from Earth to the nearest star, Proxima Centauri, is a little over 4 light-years. The diameter of our entire Milky Way galaxy is about 100,000 light-years. The Boötes Void could swallow the Milky Way billions of times over, and it is, by cosmic standards, almost completely empty. In a region of space that size, following the normal distribution of matter in the universe, you would expect to find roughly 2,000 galaxies. Some estimates suggest even more. Each of those galaxies would contain hundreds of billions of stars. Each of those stars might have planets. The numbers cascade into absurdity, trillions upon trillions of worlds that should exist within that volume of space. As of now, astronomers have counted approximately 60 galaxies inside the Boötes Void, 60, scattered across 330 million light-years. The average distance between those galaxies is about 10 million light-years, roughly 4 times the distance between the Milky Way and Andromeda, our nearest large galactic neighbor. But those 60 galaxies are not evenly distributed. They cluster in a narrow, tube-like structure running through the void, possibly the remnants of the boundaries between smaller voids that merged over cosmic time. Large portions of the Boötes Void contain nothing at all. Astronomer Greg Aldering once put the scale into haunting perspective. If the Milky Way had been in the center of the Boötes Void, he said, we wouldn't have known there were other galaxies until the 1960s. Think about what that means. Edwin Hubble proved that galaxies beyond our own exist in 1924. Using the 100-inch Hooker telescope at Mount Wilson Observatory, the most powerful telescope of its era, he observed a variable star in what was then called the Andromeda Nebula and calculated that it was far too distant to be part of the Milky Way. With that single observation, Hubble shattered humanity's conception of the cosmos. We were not alone in the universe. Our galaxy was one of many. But if the Milky Way had been located at the center of the Boötes Void, Hubble would have seen nothing. Neither would any astronomer who came after him. For decades, perhaps for centuries, humanity would have looked up at an empty sky and concluded with perfect confidence that we were the only galaxy in existence. The universe, as far as we would know, ended at the edge of our own spiral arms. Now, I need you to understand something about what empty means in the context of cosmic voids. Space, even in the densest regions of the universe, is almost entirely vacuum. The air you're breathing right now contains roughly 25 billion molecules per cubic centimeter. The space between planets in our solar system contains perhaps 10 million particles per cubic meter, mostly hydrogen atoms adrift in the solar wind. Move out to interstellar space, the vast reaches between stars within a galaxy, and the density drops to about 1 atom per cubic centimeter. 1 hydrogen atom alone in a space roughly the size of a sugar cube. Now move beyond the galaxy into intergalactic space. Here, the density falls to about 1 atom per cubic meter. 1 hydrogen atom in a space the size of a small closet. This is the intergalactic medium, a thin hot plasma of primordial hydrogen and helium spread between the cosmic filaments where galaxies cluster. But inside a void, the density is lower still. The European Space Agency describes these regions as wastelands, where outside of the rare presence of an isolated galaxy, there exists very little matter, about 1 atom per cubic meter. Some estimates suggest the density in the deepest parts of cosmic voids may be even lower, perhaps 1/10 of that. We are talking about spaces where you could travel for billions of miles and encounter literally nothing. Not just nothing you could see, nothing at all. This is not emptiness as humans understand it. This is emptiness as a physical state approaching the theoretical limit of what emptiness can be. And yet, even in the Boötes Void, something exists. In 2015, the European Space Agency released a haunting image from the Hubble Space Telescope. It showed a spiral galaxy designated MCG plus 01-02-015, a designation so clinical, so devoid of poetry, that it seems almost deliberately ironic, because this galaxy has earned another name, the loneliest galaxy in the universe. MCG plus 01-02-015 is a barred spiral, not unlike our own Milky Way. It contains billions of stars, presumably with their own planets, their own moons, their own potential for life. When you look at the Hubble image, the galaxy appears surrounded by dozens of other galaxies, bright points of light scattered across the background. But this is, in the words of the European Space Agency, a cruel trick of perspective. Those background galaxies are far, far behind this lonely spiral, separated from it by hundreds of millions of light years. They are not companions. They are not neighbors. They are other cities glimpsed from an airplane window, impossibly distant, utterly unreachable. This galaxy floats alone in a region of space where no other significant galaxy exists for at least 100 million light years in any direction. If you were to draw a sphere around our Milky Way with a radius of 100 million light years, you would enclose hundreds of thousands of galaxies. The local group, our immediate galactic neighborhood, contains more than 80 galaxies within just 10 million light years. The Virgo supercluster, our larger cosmic community, contains over 1,000 galaxies within 110 million light years. Draw that same sphere around the loneliest galaxy, and it would contain nothing but empty space. What would it be like to live there? Imagine a civilization arising on a planet orbiting one of that galaxy's stars. Picture their first astronomers pointing primitive telescopes at the night sky, searching for answers to the same questions that have driven human inquiry. What is the universe? How big is it? Are we alone? Their sky would be strange to us. Within their own galaxy, stars would still shine. The Milky Way, after all, appears as a beautiful band across our sky because we're inside it, looking along its disk. From within the loneliest galaxy, their galaxy would appear similarly, a river of light composed of billions of suns. That part would be familiar, but beyond the edges of their galaxy, they would see nothing. No Andromeda rising in the autumn sky, no Magellanic clouds visible from the southern hemisphere, no nearby galaxies at all. Their universe would end at the boundaries of their own spiral arms. For centuries, perhaps for millennia, they would develop science, philosophy, and religion with the fundamental assumption that their galaxy was the entire cosmos. They would be, in essence, like humanity before Hubble, but locked permanently into that limited worldview by the physical accident of their location. Eventually, their technology would advance. They would build bigger telescopes, more sensitive instruments, and one day, some version of Edwin Hubble among them would make the same discovery our Hubble made, that faint smudges of light, barely visible at the limits of their detection, are not nebulae within their galaxy. They are other galaxies, other islands of stars, impossibly far away. But whereas Hubble used a 100-inch telescope in 1924 to spot Andromeda at 2.5 million light-years, their astronomers would need something far more powerful. The nearest galaxies visible to them would be 100 times more distant than Andromeda is to us. They would have needed 1960s level technology, if not later, to make that discovery. And the discovery, when it came, would be profoundly different from ours. When Hubble revealed the existence of other galaxies, he also revealed a universe teeming with them. Galaxies everywhere, billions of galaxies in every direction. The cosmos exploded from a single island of stars into an ocean of archipelagos beyond counting. For the astronomers of the loneliest galaxy, the revelation would be far more bitter. Yes, other galaxies exist, but they are so far away, hundreds of millions of light years in most cases, that they might as well not exist at all. No signal could travel from their galaxy to another in any reasonable time frame. No spacecraft, no matter how advanced, could cross those distances in fewer than hundreds of millions of years. They would discover they were not alone in the universe, and then they would discover that in every meaningful sense they were. This brings us to a question that has haunted astronomers and philosophers for decades: the Fermi paradox. In 1950, physicist Enrico Fermi sat down to lunch with colleagues at Los Alamos National Laboratory. The conversation turned, as conversations among physicists often do, to extraterrestrial life. Given the vast age of the universe, nearly 14 billion years, and the vast number of stars, hundreds of billions in our galaxy alone, and hundreds of billions of galaxies beyond that, it seemed statistically inevitable that intelligent life had arisen elsewhere. Many times, perhaps countless times. Some of those civilizations should be far older and more advanced than ours. They should have had plenty of time to develop interstellar travel, to colonize their home galaxy, to spread from star to star across millions of years, even at modest speeds, a fraction of the speed of light. A sufficiently motivated civilization could colonize an entire galaxy in just a few million years, a cosmic eye blink, and yet we see no evidence of them, no signals, no megastructures, no artifacts. The galaxy, as far as we can tell, is silent. Where is everybody? Fermi asked. The question has sparked decades of speculation. Perhaps intelligent life is far rarer than we imagine. Perhaps civilizations tend to destroy themselves before they can spread. Perhaps they're here, watching us, choosing not to make contact. Perhaps we're simply listening wrong, searching for signals in the wrong frequencies, looking in the wrong places. But there's another possibility that the Boötes Void forces us to consider. What if the galaxy isn't silent everywhere? What if we're simply in a quiet neighborhood? Here is something to consider. The Fermi paradox assumes that civilizations want to communicate, that they want to be found, that they want to spread across the stars. But what if that assumption is wrong? A civilization in a void galaxy, separated from its nearest neighbor by 100 million light-years, would have no reason to believe that intergalactic communication is possible. Any signal they send would take longer to arrive than their entire recorded history. Any response would take longer still. The round-trip time for a simple hello would exceed the age of some stars. Under those conditions, would a civilization even try to communicate? Perhaps they would. Perhaps the impulse to reach out, to connect, to know that we are not alone, is universal among intelligent species. Perhaps even knowing that no response could come within 1 million generations, they would broadcast anyway. A message of hope, a bottle cast into an infinite ocean. Or perhaps they wouldn't. Perhaps they would turn inward, focusing on their own galaxy, their own stars, their own worlds. Perhaps they would develop a philosophy of cosmic acceptance, finding meaning not in connection with others, but in the richness of their own existence. Perhaps loneliness would cease to be loneliness and become simply the way things are. We cannot know what choices a void civilization would make. We can only know that the choices available to them would be profoundly different from our own. For us, the Fermi paradox is a mystery. For them, it would be an inevitability. Of course, the sky is silent. Of course, no one has visited. Of course, we are alone. The distances are simply too far. The Milky Way, as it turns out, may not be as typical as we once assumed. In 2013, astronomers Ryan Keenan, Amy Barger, and Lennox Cowie published a study suggesting that our galaxy sits inside something called the KBC Void, an enormous, underdense region, roughly 2 billion light-years in diameter. The KBC Void is not a true void like Boötes. It still contains galaxies, including the Milky Way, the Local Group, and much of the Laniakea supercluster. But compared to surrounding regions, the KBC Void is roughly 20 to 50% less dense. We are, in a sense, on the outskirts of cosmic civilization. This discovery has profound implications. If the KBC Void is real, and subsequent observations have strengthened the case, then our view of the universe may be subtly distorted. Galaxies within a void experience gravitational pulls from the denser regions beyond its boundaries. This creates an outward flow, a kind of cosmic draft that carries matter toward the void's edges. This outward flow affects how we measure the universe's expansion. You may have heard of the Hubble constant, the number that describes how fast distant galaxies are receding from us due to the universe's expansion. For decades, astronomers have been puzzled by a discrepancy. Measurements of the Hubble constant using nearby galaxies give a higher value than the measurements using the cosmic microwave background radiation from the early universe. This discrepancy, known as the Hubble tension, has resisted explanation. Some researchers now believe the KBC Void might be responsible. If we're inside a significant underdensity, the local expansion rate would appear faster than the cosmic average. Exactly what we observe. The void wouldn't change how fast the universe is actually expanding, but it would change how fast it appears to be expanding from our vantage point. This would be deeply ironic. For centuries, humans assumed the Earth was the center of the universe. We were wrong. Then we assumed the sun was special. Wrong again. Then we assumed our galaxy was unique. Still wrong. At each step, we've discovered that we occupy a perfectly ordinary corner of an impossibly vast cosmos. But now we're discovering something different. We may occupy an unusually empty corner of an impossibly vast cosmos, not special in the sense of being central or important, but special in the sense of being isolated, a quiet room in a noisy building, a country road far from the urban sprawl. We are, it seems, cosmically rural, and we are also adjacent to an even emptier region, the local void, a separate structure roughly 150 million light-years across that borders our local group. The Milky Way is actually being pushed away from this void, repelled by the absence of matter behind us, even as we're drawn toward denser regions ahead. The universe, it turns out, is not evenly distributed. Matter clumps along vast filaments, the threads of something astronomers call the cosmic web. At the intersections of these filaments, galaxy clusters form, dense concentrations of thousands of galaxies swimming in halos of dark matter. Between the filaments stretch immense voids where galaxies are sparse and matter is thin. This structure emerged from the earliest moments of the universe. In the first fraction of a second after the Big Bang, the cosmos was impossibly small, impossibly hot, and almost perfectly uniform. Almost. Quantum fluctuations, tiny random variations in the density of matter and energy on subatomic scales, were frozen into the fabric of reality during a period of exponential expansion called cosmic inflation. These fluctuations were minuscule, variations of 1 part in 100,000. To put that in perspective, if the average density of matter in the early universe was represented by a meter stick, these fluctuations would be variations of less than 1/100th of a millimeter. Almost nothing, but they were enough. The universe is ruled by positive feedback loops. In regions slightly denser than average, gravity began to pull matter together. These overdense regions attracted more matter, becoming denser still. Their increased density strengthened their gravitational pull, attracting even more matter. Over billions of years, this runaway process built the first stars, the first galaxies, and eventually the vast clusters and superclusters we observe today. Meanwhile, regions slightly less dense than average experienced the opposite effect. They had less gravitational pull than their surroundings. Matter drained away from them toward the denser regions nearby, leaving behind ever larger voids. As time passed, the voids expanded while the filaments contracted, a cosmic sorting process that separated the universe into full and empty, thick and thin. The cosmic microwave background radiation, that faint glow of light left over from when the universe was only 380,000 years old, carries a map of these primordial density variations. When scientists at NASA and ESA studied the cosmic microwave background with satellites like WMAP and Planck, they saw the seeds of everything: the slightly warmer regions that would become voids, the slightly cooler regions that would become galaxy clusters. Everything we see today, every star, every galaxy, every void, was encoded in those quantum fluctuations. The universe was programmed to develop structure. It was programmed to develop emptiness. Over billions of years, these processes sculpted the universe into its present form, a vast network of filaments and walls surrounding bubble-like voids with galaxy clusters sitting like pearls at the intersections. The Boötes Void is thought to have formed through the merger of several smaller voids. As the universe expanded, the boundaries between these bubbles thinned and eventually broke down, creating a single supervoid of extraordinary size. The galaxies that now exist within it are likely the remnants of those former boundaries, the few survivors of a cosmic consolidation that left almost everything else behind. Galaxies that form in voids are strange, isolated things. Recent research has shown that void galaxies differ from their counterparts in denser environments. They tend to be bluer, with higher rates of star formation relative to their mass. They contain younger stellar populations and lower metallicities, meaning they have fewer of the heavier elements that are forged in stellar interiors and spread by supernova explosions. This makes sense when you consider their histories. In dense environments, galaxies frequently interact. They merge with neighbors, stripping gas and triggering starbursts. They pass through galaxy clusters, experiencing ram pressure stripping, as hot intra-cluster gas tears away their own gas reservoirs. They grow through a process of hierarchical assembly, smaller galaxies accreting onto larger ones over billions of years. Void galaxies experience almost none of this. They evolve in isolation, following their own internal dynamics, building stars from whatever primordial gas was available in their local region since the beginning of cosmic time. They are like islands cut off from the mainland, developing their own unique ecosystems, uninfluenced by events in the broader world. But wait, there's another layer to this loneliness that we haven't fully explored. Consider what it takes for a galaxy to exist in a void in the first place. When astronomers first discovered the Boötes Void in 1981, they were baffled by its mere existence. The void was so large, so empty, that it seemed to challenge the standard model of cosmology. If the universe evolved from nearly uniform initial conditions through gravitational collapse, how could such an enormous underdense region have formed? The answer lies in the merging of smaller voids. Computer simulations of cosmic structure formation show that as the universe evolves, small voids, the spaces between individual galaxy groups, can combine into larger voids. Their boundaries dissolve. Their emptiness consolidates. Over billions of years, a patchwork of modest underdensities can merge into a super void of spectacular proportions. But this process has consequences for any galaxies caught in the middle. Imagine a galaxy forming near the boundary between two smaller voids. For billions of years, it exists in a relatively normal cosmic environment, surrounded by other galaxies, embedded in the filamentary structure of the cosmic web. Then, gradually, the voids on either side begin to expand. Matter drains away. Neighboring galaxies drift outward, pulled toward the denser regions beyond the void boundaries. The galaxy watches its neighbors disappear. One by one, over cosmic time, the surrounding galaxies dim and vanish, not destroyed, but simply carried away by the relentless expansion. The galaxy that remains is not special in any fundamental way. It is not more massive, not more stable, not more suited to survival. It simply happened to be positioned in the wrong place at the wrong time, at the center of a void merger event that left it stranded. This is possibly the origin of the galaxies we find in the Boötes Void today. They are remnants, leftovers, galaxies that were left behind when the boundaries of smaller voids dissolved and the surrounding matter was swept away. They did not choose isolation. Isolation chose them. There is a theory among some astrophysicists that void galaxies represent some of the most pristine examples of galactic evolution in the universe. In denser environments, Galaxies are constantly being shaped by external forces. They collide and merge with neighbors, triggering explosive bursts of star formation. They pass through the hot, dense gas of galaxy clusters, experiencing ram pressure stripping that tears away their fuel for future stars. They feel the tidal pull of nearby massive galaxies, distorting their structure and disrupting their orbits. Void galaxies experience almost none of this. They evolve in isolation, following their own internal dynamics, building stars from whatever primordial gas was available in their local region since the beginning of cosmic time. They are like islands, cut off from the mainland, developing their own unique ecosystems, uninfluenced by events in the broader world. Recent studies using integral field spectroscopy, a technique that allows astronomers to measure the light from different parts of a galaxy simultaneously, have revealed that void galaxies tend to have distinct properties. They show evidence of younger stellar populations, suggesting more recent star formation. They have lower metallicity, meaning fewer of the heavy elements forged in stellar cores and supernova. And they often display bluer colors, indicating hot, young stars dominating their light. These characteristics make sense. Without major mergers to trigger starbursts, void galaxies form stars at a slower, steadier pace. Without enriched gas flowing in from neighboring galaxies, they work with what they have, the relatively pristine hydrogen and helium that has existed since the universe was young. They are, in a sense, relics of an earlier cosmic era, carrying in their chemistry the signature of primordial conditions. But this also has implications for the possibility of life. Life as we know it requires heavy elements: carbon, oxygen, nitrogen, iron. These elements are not primordial. They were forged in the hearts of stars and scattered across the cosmos when those stars died. The more a galaxy has been enriched by stellar death, the more raw material it has for building rocky planets, complex molecules, and eventually living things. Void galaxies are element poor. Their isolation has not only separated them from other galaxies, it has separated them from the heavy elements that fuel complex chemistry. Any planets that form in void galaxies would, on average, be less mineral-rich than Earth. Any life that arose there would have to work with fewer building blocks. This doesn't make life impossible in void galaxies, but it makes it less likely. It adds another layer of cosmic disadvantage to the profound spatial isolation these galaxies already experience. Let us dwell for a moment on the experience of time in a void. We measure time by change. The rotation of the Earth gives us days. The orbit around the Sun gives us years. The rise and fall of civilizations, the evolution of species, the drifting of continents. All these changes mark the passage of time on human and geological scales. But in the deepest parts of a void, there is almost nothing to change. No galaxies passing by in the distance. No gravitational interactions to disturb the motions of stars. No new matter flowing in from cosmic filaments. The void galaxy simply sits, spinning slowly in an eternal night, its stars aging and dying without external witness. Time in such a place would take on a different character. Astronomers have speculated about what astronomy would be like for a civilization in a void galaxy. Without nearby neighbors, they would have few reference points for measuring cosmic distances. The techniques that allowed Edwin Hubble to measure the distance to Andromeda, using Cepheid variable stars as standard candles, require being able to observe those stars in other galaxies A void civilization might never develop these techniques because they would have no nearby galaxies in which to apply them. Their cosmology would be stunted. They might know that other galaxies exist out there in the unimaginable distance, but they would have no way to measure how far, no way to determine whether the universe is expanding or static, no way to detect the cosmic microwave background radiation, that faint afterglow of the Big Bang, which requires precise measurements of temperature fluctuations across the sky. A void civilization might look out at the cosmos and see only mystery. They would know they were not alone in the universe, but they would know almost nothing else. There is a thought experiment that cosmologists sometimes engage in. What would we think if we had no neighbors? Imagine humanity's history, but with one change. The Milky Way exists alone in a void, no local group, no Andromeda visible to the naked eye, no Magellanic clouds glowing in the southern sky. How would our science have developed? For most of human history, it wouldn't have mattered. The stars within our own galaxy are visible regardless of our cosmic neighborhood. Constellations would still pattern the sky. The Milky Way would still band across the heavens. The motions of planets would still inspire calendars and mathematics. But when telescopes arrived, things would change. In our actual history, the first telescopes revealed that the Milky Way was made of stars, millions of them, packed together in a glowing river. They revealed the planets in new detail, showing moons and phases and rings. And they revealed the spiral nebula, fuzzy patches of light that some astronomers suspected were other galaxies. In the void version of history, the spiral nebula would not exist, or rather, they would exist, but so far away that no telescope of the 17th, 18th, or 19th century could detect them. The early development of astronomy would proceed normally, but when astronomers began to ask, what lies beyond the Milky Way? The answer would appear to be nothing. The Great Debate of 1920, in which astronomers argued about whether the spiral nebulae were inside or outside our galaxy, would never have occurred. There would be no spiral nebulae to debate. The question of whether other galaxies exist would remain purely theoretical, a philosophical speculation without observational grounding. It wasn't until the 1960s, by Greg Aldering's estimate, that technology would have advanced enough to detect the distant galaxies at the edge of the void. By then, astronomy would have developed in a fundamentally different direction. Cosmology, the study of the universe as a whole, might not exist as a discipline. Instead, astronomers would study the Milky Way and nothing else, because as far as they could tell, the Milky Way was all there was. When the first distant galaxies were finally detected, the discovery would be shattering. Not exhilarating, as it was for us, but devastating. Humanity would learn that other galaxies exist, but they would simultaneously learn that those galaxies are unreachably far away. The expansion of our cosmic horizons would be accompanied by an immediate contraction of our cosmic possibilities. We would discover the universe and lose it in the same moment. This brings us to one of the deepest questions that the existence of cosmic voids forces us to confront. What is the purpose of the universe? I don't mean purpose in a theological sense. I mean something simpler. Does the universe have a structure that favors the emergence and spread of intelligent life? Or is life just an accident, a brief flicker in an overwhelmingly hostile cosmos. The existence of voids suggests the latter. Most of the universe, by volume, is empty. Not just empty of matter, but empty of potential. The voids cannot support the formation of stars, planets, or life. They are deserts on a cosmic scale, making up 80% of the total volume of the observable universe. If you scattered points randomly throughout the cosmos, most of them would land in voids. Most of them would land in nothing. Life, if it exists elsewhere, is concentrated along the filaments, in the narrow threads and crowded intersections where matter pools. Life is not distributed throughout the universe. Life is huddled together in the cosmic equivalent of oases, surrounded by vast expanses of lifeless desert. And even within those oases, life may be rare. The Fermi paradox asks why we haven't detected other civilizations. But perhaps the question has a simpler answer than we've imagined. Perhaps civilizations are common enough, but the universe is so big and the habitable regions so isolated from each other that no civilization can ever reach another. Perhaps we are all stranded on our separate islands, waving at the distant lights of ships we can never board. The inhabitants of the loneliest galaxy, if they exist, would understand this instinctively. Their isolation is not ambiguous, it is absolute. They can see other galaxies in the distance, but they can never reach them. They can imagine other life forms, but they can never meet them. For them, the Fermi paradox has a clear answer. Everyone is too far away. But let us also consider another possibility, one that transforms isolation from a curse into a blessing. A civilization in a void would be, in effect, invisible to the rest of the universe. In the dense regions of the cosmic web, galaxies interact. They merge, they collide, they exert gravitational influences on each other that can trigger starbursts, disrupt planetary systems, and potentially sterilize entire worlds. In galaxy clusters, the environment is harsh, filled with hot gas, intense radiation, and frequent gravitational disturbances. A void galaxy experiences none of this. It sits in cosmic silence, undisturbed by external forces. Any civilization that arose there would be protected from the catastrophic events that might threaten civilizations elsewhere. No nearby supernova to irradiate their planet. No passing galaxy to gravitationally destabilize their solar system. No active galactic nucleus to flood their neighborhood with lethal radiation. In the dark forest hypothesis, the idea that intelligent civilizations stay hidden to avoid detection by potentially hostile neighbors. A void galaxy would be the ultimate sanctuary, not because its inhabitants chose to hide, but because the universe hid them. If there are ancient, advanced civilizations somewhere in the cosmos, civilizations that have survived for billions of years, perhaps they survive precisely because they are isolated. Perhaps longevity and loneliness go together. Perhaps the civilizations that endure are the ones that never had neighbors to fear. There is one more aspect of cosmic voids that we must explore: their role in the future of the universe. As dark energy accelerates the expansion of the cosmos, voids are growing. The matter in filaments is being stretched thinner. The distances between unbound structures are increasing at an ever faster rate. In approximately 100 billion years, a span of time roughly 7 times longer than the current age of the universe, the cosmic web will have effectively dissolved. Galaxy clusters that are not gravitationally bound will have drifted so far apart that light from one can no longer reach another. The observable universe for any civilization that exists at that time will contain only its local galaxy cluster. Everything else will have vanished beyond the cosmic horizon. This is not science fiction. This is the straightforward extrapolation of current physics. Dark energy is real. Its effects have been measured. The universe is accelerating. This has been confirmed by multiple independent observations. The future of the cosmos is isolation. The Boötes Void, in this sense, is not an anomaly. It is a preview. It shows us what the universe will look like everywhere, given enough time. A cosmos of isolated structures, each one alone in its bubble of space-time, unable to see or reach anything beyond its horizon. Every galaxy will become a void galaxy. Every civilization will become the loneliest civilization. This is the ultimate fate of intelligent life in the universe, assuming intelligent life survives that long. Not destruction, but isolation. Not fire, but ice. The slow, inexorable drift into cosmic solitude. And now I must tell you something even more unsettling. The Boötes Void is not the emptiest place in the universe. It is simply the largest void we have conclusively identified. Voids, as a category, dominate the structure of the cosmos. They make up approximately 80% of the observable universe by volume. Most of space is not galaxies, not stars, not planets. Most of space is nothing. The Eridanus supervoid, potentially 1.8 billion light-years across, may be even larger than the Boötes Void, though its exact extent is still debated. Other voids pepper the cosmic web in every direction, vast bubbles of emptiness separated by thin filaments of matter. And the universe is getting emptier due to dark energy, a mysterious force that makes up roughly 69% of the total energy content of the cosmos. The expansion of the universe is accelerating. Over time, the voids are growing, the filaments are thinning. Galaxies that are not gravitationally bound to each other are drifting apart at ever-increasing speeds. In the far future, hundreds of billions of years from now, the universe as we know it will be unrecognizable. Galaxy clusters will merge into single supergalaxies, but the supergalaxies themselves will drift apart until each one sits alone in its own cosmic bubble, surrounded by horizons beyond which nothing can be seen. The cosmic microwave background radiation, that faint echo of the Big Bang, will redshift into undetectability. The light from distant galaxies will stretch until it disappears. Any civilization that arises in that far future will look up at a night sky containing only their own galaxy. They will see no evidence of the larger universe, no hint of the billions of galaxies that once existed. They will conclude, perhaps inevitably, that their galaxy is the entirety of existence. They will be in the same position as the hypothetical astronomers of the loneliest galaxy, except it will be true for everyone. The entire universe will become a Boötes Void. We are privileged, then, to live when we do. We exist in a brief window of cosmic history, a few billion years, perhaps a few trillion, when the universe reveals its structure to those with eyes to see. We can look out from our small planet, orbiting an ordinary star in an average spiral galaxy, and we can see the cosmic web in all its glory. We can map the filaments. We can count the galaxies. We can know that we are part of something vast, something ancient, something impossibly beautiful. The inhabitants of the loneliest galaxy cannot see what we see, and the inhabitants of the far future, if there are any, will not see it either. We occupy a middle place, a temperate zone of cosmic time, where the universe is neither too young to have formed structure, nor too old to have lost it. We are the species that happen to arise at precisely the right moment to ask the biggest questions and receive meaningful answers. This is not a reason for despair. It is a reason for awe. Consider for a moment our cosmic neighborhood. The Milky Way is not alone. It belongs to a gravitationally bound collection called the Local Group, containing more than 80 galaxies within about 10 million light-years. Most of these are small, dwarf galaxies, irregular galaxies, satellite galaxies, orbiting larger hosts. But the Local Group also contains Andromeda, a spiral galaxy slightly larger than our own, and Triangulum, another spiral about 2.7 million light-years away. Beyond the Local Group lies the Virgo supercluster, a vast collection of galaxy groups and clusters spanning about 110 million light-years. The Virgo cluster itself, at the heart of this supercluster, contains over 1,500 galaxies, ellipticals, spirals, irregulars, all bound together by gravity into a cosmic metropolis. And beyond Virgo, the Laniakea supercluster, identified in 2014, which contains the Virgo supercluster and more than 100,000 galaxies stretching across 500 million light-years. Our cosmic address, if we were to write it out, would read something like Earth, Solar System, Orion Arm, Milky Way Galaxy, Local Group, Virgo Supercluster, Laniakea Supercluster. We are embedded in structure at every scale. At night, when we look up at the sky, we see stars, our neighbors in the Milky Way. With binoculars, we can see the Andromeda Galaxy as a faint smudge of light. With larger telescopes, we can resolve individual stars in nearby galaxies, map the distribution of dark matter through gravitational lensing, detect the faint glow of the cosmic microwave background. The universe reveals itself to us because we are located where we can see it. An astronomer in the loneliest galaxy would have a very different experience. They would see their own galaxy, the stars, the nebulae, the spiral arms. But beyond that, they would see almost nothing. The nearest large structures would be so faint, so distant, that detecting them would require technology far beyond what we possess today. Their sky would end at the edge of their galaxy. Ours extends to the edge of the observable universe, 46 billion light-years in every direction. This is not because we are special. It is because we are lucky. We happen to form in a region where galaxies cluster, where the cosmic web is thick with structure, where light and matter and information flow between neighbors. The loneliest galaxy happened to form where there is nothing. There is a famous photograph called the Pale Blue Dot, taken by Voyager 1 on February 14th, 1990, from a distance of about 6 billion kilometers. It shows Earth as a tiny speck, less than a single pixel in size, suspended in a beam of scattered sunlight. Carl Sagan, who had requested the photograph, wrote movingly about its implications. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The pale blue dot humbles us. It shows how small we are against the vastness of even our own solar system. But consider this. If that photograph had been taken from the loneliest galaxy, looking back at their home planet from a similar distance within their own solar system, they would see a similar image. A pale dot, a fragile world, home. The emotional resonance would be the same. The sense of perspective, the recognition of smallness, the awareness of preciousness. These would be universal. But if they then turned their gaze outward, away from their planet, and looked at the wider universe, they would see nothing like what we see. No neighboring galaxies, no cosmic web, no sprawling tapestry of light and matter, just darkness. Their pale blue dot would float in a void. There is a concept in psychology called the overview effect. Astronauts who have seen Earth from space often describe a profound shift in perspective, a sudden, visceral understanding of the planet's fragility and unity. The borders that divide nations become invisible. The conflicts that consume human attention seem trivial. What remains is just the planet, a blue marble suspended in blackness, home to everything we have ever known. The overview effect is transformative, precisely because it places the familiar in an unfamiliar context. We see our world from outside it, and in that seeing, we understand it differently. Studying cosmic voids offers something similar. When we look at the loneliest galaxy, that lonely spiral galaxy adrift in emptiness, we see ourselves from the outside. We see what we might have been had the cosmic dice rolled differently. We see isolation as a physical condition, measurable and real. And we understand our own connection to the cosmic web more deeply. We are embedded in structure. We have neighbors. We can look up at night and see the Milky Way blazing overhead, and beyond it, if we know where to look, the gentle glow of Andromeda. We are rich in light. Not everyone is so lucky. In the end, what does loneliness mean on a cosmic scale? For humans, loneliness is the absence of connection, the feeling of being cut off from others, isolated within our own experience. It is a social and emotional condition, painful precisely because we are social beings, evolved to seek connection. For a galaxy, loneliness has no emotional content. The loneliest galaxy does not feel lonely. Its stars burn without awareness. Its planets, if it has them, orbit without knowing they are alone. The void that surrounds it is just empty space, not a presence, not an absence, just the way things are. But if intelligent life has arisen in that galaxy, if some form of consciousness has evolved there, looked up at the sky, and asked the same questions we ask, then loneliness becomes meaningful. It becomes a condition of existence, a constraint on possibility, a fact about the universe that shapes everything. For such a civilization, loneliness would not be a feeling. It would be a law of nature. They would be alone, not because they failed to find others, but because others are too far away to find. They would be isolated not by choice or circumstance, but by the fundamental structure of space-time. Their cosmic address, written in the language of filaments and voids, would read, nowhere, near nothing, alone, and they would have to make meaning in the face of that isolation. Perhaps they would despair. Perhaps they would turn inward, creating rich cultures and philosophies that did not depend on external contact. Perhaps they would broadcast into the darkness anyway, sending messages that would take 100 million years to arrive, addressed to recipients they could never meet. Or perhaps they would simply accept it. The universe is what it is, It contains multitudes and emptiness, connection and isolation, the crowded filaments and the silent voids. To exist in a void is not better or worse than existing in a filament. It is simply different. Every location in the cosmos offers its own perspective, its own limits, its own possibilities. The loneliest galaxy in the universe is still a galaxy. It still contains billions of stars, each one a furnace of creation. It still holds the potential for life, for thought, for wonder. Its isolation does not diminish its existence. It simply makes that existence different from ours. Somewhere in the constellation Pisces, roughly 300 million light-years from Earth, a spiral galaxy floats alone. Its stars burn in silence. Its arms sweep through the darkness without witness. If there are planets there, if there is life there, it has no way of knowing that it is not the only life in the universe. But we know that this lonely galaxy exists. We have photographed it, studied it, given it a name. We have, in a sense, reached across 300 million light-years of emptiness to acknowledge its presence. And in that acknowledgement, perhaps the loneliest galaxy is a little less lonely, because somewhere, impossibly far away, impossibly different, impossibly improbable, another form of intelligent life looked up, saw a smudge of light in the void, and wondered. We are that form of life. We are the ones who wondered. And that perhaps is the answer to the loneliness at the heart of the cosmos. We cannot cross the distances. We cannot reach the worlds. But we can know they are there. We can imagine what it would be like to stand beneath an empty sky. We can feel, in some small way, the weight of that solitude. And in knowing, in imagining, in feeling, we connect. Across billions of light years, across billions of years, we are all alone, together. The universe does not care about our loneliness. It does not arrange itself for our comfort or our comprehension. It simply is, vast beyond measure, old beyond reckoning, indifferent to the small sparks of consciousness that flicker briefly on a few of its worlds. But we care. We have looked into the void, not metaphorically, but literally. And we have found it terrifying and beautiful in equal measure. We have discovered that emptiness can have structure, that nothing can have geography, that absence can be measured in millions of light years. The Boötes Void, the great nothing, the loneliest place in the observable universe. It is out there, right now, as you read these words. It has been there for billions of years. It will be there for billions more, growing slowly larger as the universe expands, swallowing the thin filaments of matter at its edges, trending inexorably toward a future where everywhere is like this, where every galaxy is the loneliest galaxy. But not yet, not for us. Tonight, if the sky is clear, you can step outside and look up. You will see stars, thousands of them, the band of the Milky Way, perhaps even the faint smudge of Andromeda, our galactic neighbor, visible to the naked eye across 2.5 million light-years of space. You are not alone. You have never been alone. The universe placed you here, on this planet, in this galaxy, surrounded by a web of light and matter, stretching in every direction. You are part of something, a structure, a pattern, a story that began with quantum fluctuations in the first fraction of a second and continues to unfold today. The inhabitants of the loneliest galaxy, if they exist, cannot say the same. For them, the universe is a different place, a quieter place, a place where the distances are too vast and the neighbors too few, and the darkness stretches on forever. We don't know if anyone lives there. We don't know if anyone has ever looked up from a planet in that lonely galaxy and wondered what lies beyond the edge of the starlight. We don't know if they have felt the ache of cosmic isolation or found peace in cosmic solitude. But we can imagine, and in imagining, we learn something about ourselves. We learn that connection is not guaranteed. We learn that structure is precious. We learn that the light in our sky, the stars, the galaxies, the faint glow of distant superclusters, is a gift of location, an accident of cosmic geography that could easily have been otherwise. The sky is full of light, and somewhere in the direction of Boötes, there is a galaxy that cannot say the same. A galaxy that exists in a cosmic silence so profound that the light of the nearest neighbor takes 100 million years to arrive. Remember it when you look up. Remember that the universe could have placed you there, and it didn't. The stars are calling. Listen, we are the ones who can hear them. That is our gift and our privilege and our responsibility to be the universe's way of knowing itself. Here in this crowded corner of the cosmic web, surrounded by neighbors, swimming in light. The loneliest place in the observable universe is real. It exists. It waits, but it is not our home. We live elsewhere. We live in the light.